In this section, we're going to be looking at z-scores. Now, a z-score is a measure of position that describes the location of a value in relation to the mean. Now, if you think that sounds a lot like the standard deviation, you are correct. However, we're going to see the z-score has some important differences from the standard deviation that allows us to do some comparisons we can't do with just the standard deviation alone. First of all, a z-score has no units of measure, so that's an important difference. And as we can see here on the right, we have our formulas. We still have a formula for both a sample and we have a different formula for the population. So take a moment and look at these and tell me which one you think goes with which criteria. If you saw the one on the top is for a sample, you're correct. Here we can see our X bar and our standard deviation symbols that are used for a sample. The one on the bottom has the symbols for a population. Notice again, the formulas are exactly the same as far as the computations go. Now, when we're looking at the z-scores, the z-score determines an unusual value if they are -2 or greater than 2. So a z-score of -2.1 would be seen to be unusual, as would a z-score of 2.2. Now, this matches with the -2 standard deviations and the +2 standard deviation unusual value parameters set by the empirical rule. So the exact same parameters. So why then do we take the extra effort to convert to a z-score? What would be the point? Well, this is where z-scores allow us to do something that we can't do otherwise. Because with z-scores, we can compare the values from two different samples or populations. This becomes really important if I'm wanting to work with groups that have different means or standard deviations or different sample sizes. All of these can be very important, and I want to be able to make comparisons across them in real life. And in order to do that, I'm going to have to convert them to z-scores. So let's take a look at how we do this. And we're going to work through practice problem in your book, number 14 on page 125. So this question here is asking, relative to their genders, who was younger when winning the Oscar, Sandra Bullock or Jeff Bridges? Here's the question we need to answer. Now, notice that the criteria is related to their genders. This means it's not simply who was younger, but rather, was Sandra younger than most women when winning an Oscar, or was Jeff younger than most men winning an Oscar? So we have to make these statements within comparisons to their two different groups. All right? These two different groups have different means and standard deviations, which means that we're going to have to calculate a z-score for each of them before making the comparisons. All right, here's our z-score formula we're going to work with. Now, fortunately enough, in this problem, we have the means and the standard deviations for each group already provided in the problem. However, keep in mind, if they were not provided, we could use the summary stats option that we looked at previously in StatsCrunch to calculate them and then plug them into this formula. All right, let's take a look at what we've got here. So we've got actresses and with actors, we have both of their means and their standard deviations listed here. And if we're applying, let's work with Sandra first. So if we're applying the formula to this data and we plug it in, we're going to get this. So 45 is our X, that's Sandra's age, so it's our X value for this particular problem. All right, 35.9 is the mean age for actresses, so that is our X bar here for this problem. And then the standard deviation age for actresses is 11.1. So we plug these in, we run the calculations, and we get this answer. Now, I've made two mistakes here. Take a moment and look at the problem and identify what are they. What are two things that I've done wrong here? Give you a hint. Think about the rounding rule and the units of measure. So the rounding rule says that when we're doing a z-score, we always round to 2 decimal places. Notice this is different from some of the other rounding rules. So as I've said before, right below your z formula, you need to write down your rounding rule so you have it together. Also remember, with a z-score, we have no units of measure. So that means for my z-score for Sandra's age is going to be 0.82. Now, take this same information and run through and do the calculations for calculating the z-score for Jeff Bridges' age. When you finish those calculations, move on to the next slide and let's check it together. All right, so you should have gotten 1.77 for the z-score for Jeff Bridges' age in relation to his gender. Now let's take these and put these back into answering our problem. So when we do this, we see Sandra is younger in relation to her gender with a z-score of 0.82. Jeff has a z-score of 1.77. So he was older in relation to his gender group when winning his Oscar. Now, bonus question. Are either of their ages unusual in relation to their genders? So think about that for a moment. Remember, we would have to apply our rule for the unusual values. So take a look back at that in your notes and then answer the question and then move on. And let's check it together. The answer would be no, because both of them are within the boundaries of -2 and +2. Okay, so when we're looking at this, we can see Sandra's score 0.82 is clearly within that range, and Jeff's score of 1.77 is also still within the range of -2 to +2. So neither of them are unusual ages in relation to their gender when winning an Oscar. Now, to finish this up, let's take a look at comparing the z-scores and the empirical rule so we have a good visual for this. So here we can see the raw scores for for actresses in Sandra Bullock's age. So we have our mean of 35.9, and then for our mean plus 1 standard deviation, then we have 35.9 plus 11.1, which gives us 470. And we've plotted Sandra's age roughly in place at age 45. All right, so here we see these on the empirical rule. Now, notice when I plug in my z-scores, my z is always going to be, my z for the mean is always going to be 0, because that's no distance from the mean. That's the actual mean, right? So then, if we move out, z of 1, meaning 1 step away from the mean, is going to correspond with 1 standard deviation from the mean with the raw data. Similarly, the z-score of 0.82 corresponds to the raw score of 45 in its location on this distribution. So what I want you to see with this is when we convert Sandra's data for actresses and her age from the raw data that we see here to the z-scores represented in the z-box, we are not changing the relative position of anything. Thus, we can then produce several different sets of z-scores, maintain the relative distance of values from each other, and then make comparisons across those z-scores. So hopefully this helps clarify for you why we use the z-scores, all right, how they relate to maintaining the location of difference of a value from the mean, but then allowing me to make that standard so I can apply that across multiple different samples or populations to make comparisons across them that are meaningful and relevant. This concludes our section on looking at z-scores. Next up, we'll be looking at percentiles.